Okay, so good morning and welcome back, everyone. Let's start the day with Thomas's lecture, where he'll continue to talk about the 3+1 decomposition of space-time, applying it to GR.
Thank you. Good morning, everybody, and welcome back. So let's just try to remember what we did yesterday. We started with a 3+1 decomposition, and we started to explore that in the context of Maxwell's equation, in the context of electrodynamics, right? And we went through various different steps. We decided that we would look at decompositions of the Faraday tensor, which we wrote as the outer derivative of this four-dimensional vector potential A. And then we first, just did a naive kind of slicing, according to our old coordinate system, but then we considered general slicing conditions. We introduced a normal vector on that. And then we thought about how can we decompose any tensor, or we started with just rank one tensor with vectors, into both their normal part and their spatial part. That introduced the projection operator. Do we all remember that? And then we had some fun with the projection operator, and we just played with that. We said, well, let's, we have a new hammer. Where are nails in the wall that we can now, use this hammer on? And the first nail that we found was this J. So we decomposed our four-dimensional charge current density J into a normal in the spatial part. And then we decided, let's be a little bit more adventurous. Let's work on a two-dimensional tensor. And we looked at the gradient of N. And that introduced us to the extrinsic curvature. Are we all good with that? Are we on board with all on the same page? Yes, thank you.
So the spatial slices labeled by T, they are not supposed to intersect.
You know what? I couldn't hear you. Could you say that again?
The spatial slices, which are labeled by T,
yeah,
they are not supposed to intersect.
Not really. Okay, so I'm being non-committal here. So basically, no, you are right. Basically, what we would like is a foliation. So we would like to actually foliate our space-time basically by these slices, and they're not supposed to intersect. You're absolutely right. Okay, otherwise you would expect something funky where they actually intersect and things are not well defined there. Okay, so that is exactly right. Okay, yeah.
But while doing the formulation, there should be a constraint on something which will not allow them to use. Should not be a
right.
Will not have an argument. Where is that?
So basically, so you're bringing up a topic that I've been quite interested in lately. That's why I'm hesitating on all of this, okay? So basically, actually, can anybody see how we could guarantee that these slices will not intersect? Because, let's see, one of the quantities that we encountered is basically, we talked about a normal observer, okay? We talked about the proper time that this normal observer measures as time advances. We talked about the proper time of a normal observer as the normal observer goes from a slice t to t plus dt. That proper time advances at what rate? In relation to the coordinate time dt. If the coordinate time dt, or if the coordinate time advances by dt, then the proper time of this normal observer advances by alpha dt, okay? So basically what you're saying is if these slices do not intersect, then that d tau better be positive. That means that the lapse should also be positive. So that would guarantee that they don't intersect, okay? Can we guarantee that globally? Well, it's certainly not, because we haven't made any statements yet about the lapse, okay? So we cannot guarantee that basically for now. In fact, actually there are some slicing conditions which allow the lapse to go negative. You think that would have horrible consequences for your code. Actually, I found that it seems to work fine, and it's kind of confusing why that is. Okay, you could argue because that would correspond to these foliations to intersect. Okay, but so for now, at least we will assume at least locally that they don't intersect. Okay, and we will basically worry about the global properties later. Okay, but excellent question. Any other questions that came up before we move on here? This was a demo, actually, because remember 2 days ago I told you that I never ask, are there any questions? And this is why, okay? Because they're never any. All right, okay, great. Okay, so basically we played with the projection operator acting on nabla n. Let's look at another rank 2 tensor, and let's again play with projecting this other tensor. Okay, actually, any thoughts on what other rank 2 tensor we encountered that we might play with? Sorry, Dave? Well, there's the metric. We'll get to that later. But in the context of ENM, there was another rank 2 tensor that really, it's the Faraday tensor, right? So let's play with the Faraday tensor. Okay, so here's our next example. The Faraday tensor. Okay, so FAB. Okay, now we want to project this Faraday tensor into both space. I almost said both. I shouldn't have said both, because what kind of parts do we expect now? We have two indices, okay? Each index we can project into a normal and a spatial part, but now we have two, so we could have a normal, we could have a mixed normal spatial, and we could have a spatial component, okay? So let's see what happens here. Now, how do we do this? We'll use the same trick as yesterday. So I'll insert 2 copies of delta, which is the same as G with an index upstairs and downstairs. So I write this as GAC GBD times FCD. Now I write the G's in terms of the projection operator and normal vectors. So this is the same as gamma AC minus NA NC times gamma BD minus NB ND times FCD. Now we have 4 terms when we multiply out all these terms. So let me write them down. Okay. The first term will be when we have 2 projection operators acting on FCD. So that gives me gamma AC, gamma BD, FCD. Okay. Then I have 2 mixed terms when I have one set of n's multiplying the gammas, either these 2 or these 2. So let me write them down. Let me start with this gamma. I have a gamma BD, NA, NC times FCD. Okay. Then I have basically a permutation of that. That would be minus gamma AC, and then I have NB, D and D times FCD. Am I doing that right? No, I think I'm mixing these up, right? So this is now gamma AC, and then NB and D, and then I have an FCD. That's right. And then I have now I have a plus because the 2 minuses cancel. NA, NB, NC, ND times FCD. You agree? Okay, you're checking my indices. Okay. Now, does anybody see what this last term is? It is 0. Actually, why is it 0? Because of symmetries, right? Basically, FCD is antisymmetric. So I get to pick up a negative sign if I flip these, but here I would get a positive sign because these are symmetric. So this term must be 0. So one term is already gone. Okay. Okay, that's actually the normal projection. So in this case, we don't have a normal projection. We only have a spatial, and then perhaps mixed spatial normal. Okay, so let me first look at this first term. Okay, let me rewrite that. But gamma AC, gamma BD, FCD, okay, that is the same as gamma AC, gamma BD times, yesterday we wrote the Faraday tensor as the outer derivative of A. So let me write this, insert this here. We had a nabla C AD minus nabla D AC, right? And we already decomposed A, okay? So I write A as gamma AC, gamma BD times. So now I'll insert what we did for A yesterday. We wrote A as phi times ND plus the spatial part, A projected or perpendicular, C, D, CD, that's right, minus nabla D, now the opposite, phi and C, minus A perpendicular C. You agree? Okay. Now, my claim is that these two terms, the nabla acting phi and d, and nabla d acting phi and c, these two terms cancel, and I assigned that as an exercise in the tutorial. So maybe you already worked that out, okay? So it basically, or look at it today, basically, or we can talk about it later if you'd like to, but these first two terms cancel. That means that I'm left only with the derivatives acting on the spatial parts A, C. Okay. Now, nobody warned me that I had a wrong sign there. Okay. Right. Okay. So now this means this is the same. Or now I have only these derivatives left over. Now, what we'll do? What is this? Basically, we're taking a four-dimensional gradient, or having the four-dimensional gradient of a covariant derivative, where they're acting on a spatial vector. But we're projecting both indices into the slice. That is now how we define the spatial covariant derivative. So this gives us an opportunity to already introduce formally the spatial covariant derivative as the following. So we define the spatial covariant derivative of spatial tensors. So I've done this kind of before. I said, oh, this is now the spatial covariant derivative, but now we will formally define this. So if I have a spatial vector A perpendicular, in this case, A spatial, then I define the spatial covariant derivative as the projection of both indices in this expression, dB, of nabla C A D perpendicular. Okay, so this is our definition. Okay. A little bit later today, we'll see how we can evaluate this derivative very nicely, okay, in a way that is completely analogous to the way that we're used to from four-dimensional covariant derivatives. But for now, we'll just accept this as our definition. And now I can use this definition to write FAB. Then, okay, oops, there we go. FAB equals, I need to do one more thing here before we do this. Does anybody see what NC FCD is? FCD, if you remember how we defined the Faraday tensor, we wrote it in terms of the electric fields and the magnetic fields, okay? And if you basically contract that Faraday tensor with the four velocity of an observer, then you get the electric field, okay? Is everybody familiar with that? Okay, if not, try it out, okay? So that's precisely what we're doing here. I'm contracting FCD with the four velocity of the normal observer. So this gives me the electric field as seen by the normal observer. Okay, so this term is, this term here is actually, it's minus ED. Why the minus? Because I would get the positive sign if I contract it with a second index, okay? Remember F is antisymmetric, okay? But here I'm contracting with the first index, so I get minus ED. Here, on the other hand, I am actually contracting with the second index, so this gives me EC, okay? All right, so basically now I write this first term as in terms of the spatial covariant derivatives, and then the last two terms I can write as simply the normal vector times the electric fields, okay? And really the spatial projection of the electric field, but the electric field is spatial already, so we can just ignore this, the spatial projection, because it's projected already. Okay, so we have FAB is then dA, A perpendicular B, minus dB, A perpendicular A, plus NA EB minus NB EA. Okay, this is antisymmetric as it should be. Okay, and now we see that this is a nice way of basically decomposing the Faraday tensor. We have a spatial part, and we have a part that is normal spatial. We have a normal vector and a spatial vector. We saw that the completely normal projection vanishes. Right? Sounds good? All right, let's revisit what we just did here. So here we said, well, I can find the electric field as seen by the normal observer by contracting the normal vector with the Faraday tensor. Let me do that again. Okay. Okay, so let's write ED as NC FCD. Okay. Now with the indices downstairs. Okay. Now, basically, what is that? That is the same as NC times nabla C AD minus nabla D AC. Okay. Yeah. What happened to the? Oh, these gammas? Okay, this gamma is contracted with ED. Okay, but ED is spatial already. So basically, when you project a spatial operator, you get the same vector again. So this just gives me EB. That's why we have an EB here. Okay. 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 Good. All right. Actually, let me just pause a second here. You could ask, why am I doing all of this? Okay. Isn't this supposed to be a course on general relativity? So why is it that we're talking about E&M here and not general relativity? Fair question. Okay. But the neat thing is, as we're going through this, we're developing all the mathematical objects that we need for GR already in the context of E&M. Okay. So we did this already yesterday, right? You notice the lapse function, the shift vector, the extremity curvature, they popped out in E&M. We did not need GR for that. Likewise, we just introduced the spatial covariant derivative. We encountered it by just looking at the decomposition of the Faraday tensor. Okay, so all these objects that we're developing here, those are exactly the tools that we need for GR. We'll do this in the context of E&M, where we see where maybe a context that we're more familiar with. Okay, that is more intuitive, and then, but in a minute, where by 1 minute I mean like 15 minutes or so, we'll switch gears, we'll talk about GR, and we'll see how we use exactly the same objects there. It's exactly the same thing, all right? So now, same thing, why do I want to do this in detail? Because in a minute, we'll again introduce a new quantity. We'll see how it appears very naturally, even E&M, and we'll use the same tool then in GR. So what am I talking about? Let's work out what this is. This is the same as NC times. Now I'll do the same thing that we did here. I'll express the four-dimensional vector potential A in terms of phi n plus the spatial projection. So let me insert this. Then I have an NC. Now we have to basically what do we get, right? For AD, I insert phi ND plus A projected D. Then I take a derivative of that. When I take a derivative of phi times n, I get two terms from the product rule. So I get two terms from each of this one plus one from this 3. Since I have two of these, I end up with a grand total of 6 terms, okay? Let's write them all down, okay? So the first term will be when I insert this and then take the derivative of n, so there will be a phi outside, and then I have a derivative nabla c and d. Okay. Then I get basically another term by acting with a nabla c on the phi term. So this will be plus and d nabla acting on c phi. Then I get the derivative acting on the spatial part, a the spatial. So that gives me a plus nabla c a perpendicular d. That completes this first term. Does that make sense? Yes.
Why did we cancel both of them?
So why do these two terms cancel? Yes, after contracting with the gammas, okay? And you can see why, because then the n's go away, right? Okay, great, good. Are we on board with these 3 terms arising from this? Then basically I need to copy the same terms again, just with C and D interchange, so and a negative sign, so that gives me a minus phi nabla D and C minus NC nabla D phi plus a minus nabla D AC. Okay, Sounds good? All right, now let me work on these terms a little bit. Okay, what do we get from that? This term, basically I can actually take the phi out, and then I have a phi times NC nabla C ND, right? There we go. That is the first term. Next, let me actually work on this term. Now, in this term, we have NC, NC. What is NC, NC? -1. That's right, so that cancels this term. So that gives me a plus nabla D phi, right? Good. So now we are done with these two terms. Now let me write down this one. I'll just leave that unchanged. So that gives me a plus ND NC nabla C phi. Okay. So now we have that one. And then, okay, how about this one? What do we get? What does that term give us? 0. Excellent. Very good. Okay, because n is normalized. We saw that yesterday, right? So we did enough projection gymnastics to recognize that as 0, right? So now we have only these two terms left. Let me write down the first one. The first one will be, this one. So I get a plus NC. Actually, you know what? I'll make this a long line. Plus NC nabla C AD projection, okay? And then I have this last term. We have an NC dotted into nabla D A perpendicular C, okay? Now I will write this down in the following way, and then we'll discuss why that is. That is the same as plus A perpendicular C nabla D NC, okay? Why am I allowed to do that? Can anybody see that? Yeah. Exactly. Exactly. It is because this is a spatial vector. So if I contract the spatial vector with a normal vector, I get 0. Okay. So that means that the derivative n times the derivative of A must be the negative of A times the derivative of n. So I can, because these are perpendicular, I'm allowed to trade them at the cost of a negative sign. That's what this is positive. Okay. All right. Now, what is this term? So basically what this term is, we've seen that yesterday. This is the same as phi times the acceleration, exactly, AD. And what you will see on the tutorial is that I can neatly write the acceleration as the spatial derivative nd dd of the logarithm of the Laplace function. That is the result that you will derive in the tutorial, okay? So basically you'll see where this comes from. Okay, so I can write the first term as this. How about the next two terms? Well, notice that in the first term, I can rewrite the first term by inserting a delta. Then I would get a G, D, C, and then a plus ND and C times the gradient of phi. You agree? But this, you recognize, is the projection operator. If I act with a projection operator on each index of the 4-dimensional covariant derivative, that just gives me the spatial covariant derivative. So this is in fact the same as, so it's the same as gamma C, nabla C phi, but that is the spatial derivative, covariant derivative, d phi. Okay. All right? That leaves us with these last two terms. Okay. Now, does anybody recognize what these last two terms, what they are? It's a funky derivative, and it's a new derivative that we're encountering here. Sorry? It is the Lie derivative of A along n. And again, why? I'll speak about my opinion here. I think it's nice to do this because you see how the Lie derivative actually very naturally appears in the context even of E and M. We're not making it up. It just pops up. Okay, so we now define the Lie derivative. Maybe I'll do it over here. We define the Lie derivative as the Lie derivative along the vector n of AD perpendicular. We define that is actually it's NC nabla C AD perpendicular plus AC perpendicular nabla D NC. Okay, that is the Lie derivative of a covariant vector. Okay, it's vector with the indices downstairs. We talked about the covariant derivative on Monday, and remember how we defined the covariant derivative? The covariant derivative measures what? Basically, the covariant derivative of a vector field is exactly 0 if that vector field is parallel transported. So basically, if you had to kind of picture, however well you can do, that basically what does the covariant derivative measures? The covariant derivative measures any deviation from parallel transport, right? So by the same token, you could ask now, what does the Lie derivative measure? Does anybody know? What does the Lie derivative measure? Yeah. Exactly. It measures basically the deviation from a simple coordinate transformation. Okay, so basically, if any changes in this field A are the result of just an infinitesimal coordinate transformation, then the Lie derivative is 0. Okay, so basically, the Lie derivative tells us what part of any changes of A are not due to just a simple coordinate transformation. That is kind of, in a nutshell, the interpretation of what the Lie derivative measures. All right, so let me write this down. It measures. Actually, I need more chalk here. It measures changes in A, D, along the normal vector N, A, that are not resulting from infinitesimal coordinate transformations. Okay, generated by NC. Okay. I will let you explore some of the properties of the Lie derivative on the homework. Okay, in the tutorials, there's some exercise where you can play with this. You will explore some of the properties. One thing that you will discover is, when you evaluate this, you could evaluate these covariant derivatives by writing out these covariant derivatives in terms of partial derivatives and Christoffel symbols. And what you will discover is that, remarkably, the Christoffel symbols will all cancel out exactly. So you don't need the Christoffel symbols to evaluate this. So in fact, what that means is you can write these covariant derivatives here in terms of any connection that you would like to. We could also replace the covariant derivatives with partial derivatives. We would get the exact same result. Okay, that's one of the things that you'll play with. Okay. Now, let me also remind you yesterday we introduced the shift vector and we introduced the normal vector, and we saw that we can basically combine those two to get the basic time vector TA as alpha NA plus beta A. And remember, this just had simple coordinates 1, 0, or components 1, 0, 0, 0. Okay. Then actually it's nice to, rather than write this in terms of the Lie derivative along the normal vector, Turns out it's actually nicer to write this in terms of the Lie derivative along alpha times the normal vector, which gives us then the Lie derivative along this t. And why is that nice? Because now basically this vector has only a component 1 here, and that means that many of those terms in the Lie derivative vanish. Okay? So let me write this down. So then I can write alpha times the Lie derivative of n of a d perpendicular. That's the same. You can check this by using that definition of the Lie derivative. You can check that this is the same as the Lie derivative along alpha n times a d perpendicular. Okay? But using the definition of alpha of t, you can then check that this is the same as the Lie derivative along this vector t of ad minus the Lie derivative along beta of AD perpendicular. Okay? And now this term is particularly simple to evaluate because when you basically do this, when you insert TA in here, you see these terms, for example, all go away. And the only term that we left here is the derivative with respect to t. Okay? So this first term, in fact, reduces to just a simple partial derivative with respect to time, t. Okay, that's all we get here. So this is the same as partial t ad perpendicular minus the Lie derivative along beta ad perpendicular. Okay, and now I can combine all of these terms to write the E field as the following. Okay. Then I get partial t a perpendicular equals minus alpha EA minus dA of alpha times phi plus the Lie derivative of beta of AD. Okay, so this is basically now the time evolution equation for A. You see what I did, right? I used this equation. We have this. I have a derivative of the labs, a derivative of phi, which are combined in the derivative of the product of those two. This gave me the Lie derivative of A, which I wrote in terms of the partial time derivative and the D derivative along beta, and that's all I got. Okay. And again, what is really nice is even in the context of ENM, we haven't even talked about GR at all. Right? Basically, we see how we encounter the Lie derivative, the spatial covariant derivative, all of these tools. In fact, basically, the evolution equation in GR that we'll see later today has a very similar form. Okay, sounds good. What is the next thing that we would have to do if we wanted to formally carry out the 3+1 decomposition of Maxwell's equations? We could go back to our notes from yesterday because we did the complete decomposition for our original coordinate system, and we did the following. We first looked at the definition of E in terms of the Faraday tensor. That gave us yesterday this evolution equation, partial A equals E minus partial phi. That was what we got yesterday when we did our, let's say, our naive 3+1 decomposition, where all slices were parallel. Okay. Now we generalized that, and guess what? We got a generalization of that, which is this. Okay. Again, we got that simply from identifying E with a projection of the Faraday tensor. What did we do next? Next, we looked at both the time and the space components of our field equation, and that gave us the space component, gave us the constraint equation. The spatial components gave us the evolution equation. Okay? Again, the space component gave us this constraint equation. The spatial components gave us this evolution equation. So if we now want to get the generalizations of these two equations, we would do the same thing. We would decompose the Maxwell's equations, our field equation, okay, in terms of the spatial normal parts. That's a little bit of a calculation. At least for now. Yes, go ahead.
How it came out to be that derivative alpha m, how like just
Yeah.
the second line.
Yeah. So you're talking about this equality? Okay. So basically, this is why is it that I can pull the alpha into the n, right? Is that what you're asking? And basically, I didn't give you an explanation. What I told is you can check this. Okay. So but it's non-trivial. Okay. So basically, is that always true? Well, it only works for covariant spatial. So I'm sweeping a few steps under the rug. But what you can do, like if you're bored silly tonight, say, okay, and you really didn't know what else to do, you could check this, okay? And what you would do is you would evaluate this Lie derivative, and you would compare it with the Lie derivative of alpha n, and then you would have an extra alpha here, and you would have an extra alpha here, and you would see in what cases that is the same as that, okay? So that's actually a very useful exercise to do. Yeah, good. All right? Okay, so let me write down what we would have to do next. So next up is we would decompose our field equation, which yesterday I called En. Okay, that is in your notes, so you can look it up. Okay, what was the field equation? It was the divergence of FAB equals, okay, actually yesterday I wrote this, I introduced this funky ENM tidal tensor, okay? This is the same as 4 pi JA. And the right-hand side, we have already decomposed. That's the first thing that we did, right? So the right-hand side, we can, maybe there's a minus, it's minus 4 pi rho NA plus J perpendicular A, okay? So the right-hand side, we've already decomposed into a normal part and a spatial part. Now we would have to decompose the left-hand side. How do we do that? Well, there's one free index, which is the B. We would write that index by inserting a delta, okay, and delta AC or something like that. Then we write the delta as basically this projection operator plus the normal terms, and then there's a fair bit of math to do. And what you find by the end of the day is this. We would find that FAB equals, okay, so this is the same as nabla AB minus nabla B AA, okay. What this ends up being is alpha to the minus 1, dA alpha dA AB minus alpha dB AA perpendicular, okay, plus gamma BA, the Lie derivative along n of EA, minus EB times the trace of the extended curvature, minus NB dA EA. Okay, so basically I decided to skip the derivation of that for now. If we have time at the end of the lecture today, we could go back to that. So you feel free to ask me about it. I'd be happy to show you how to do that. Okay, but let's instead, for now, let's think about why should we have anticipated something like this? Let's think about what kind of derivatives are hidden in here. So we're taking derivatives of this 4-vector A. And what kind of derivatives do we encounter? Well, there will be A, okay, the indices A and B take both spatial and time values. So we certainly get second space derivatives, but we also get mixed space and time derivatives, and we get 2 time derivatives, okay? Now, what is neat here is that the first term we're getting is kind of the spatial cousin of this operator, right? Basically, these are all space-time operators. Now we get the same thing with spatial operators. The only difference is there's this extra alpha popping up here. That alpha appears because these are covariant derivatives. If these were partial derivatives, the alphas wouldn't even be there, okay? So the first term captures all the spatial derivatives. So now we're done with the spatial derivatives, okay? But it's also clear that this part alone cannot capture all the properties of this because there's no room here for any time derivatives. So we need somewhere else to get to time derivatives, okay? Now, where are time derivatives of A? Well, time derivatives of A are hidden in E. So if we have a term just with an E, okay, like this one, that gives us a time derivative, okay? Now, basically, then you could ask, okay, we also need mixed time and space derivatives. Well, there's one here, right? Because E has a time derivative of A, and then we're taking a spatial derivative. Okay. Then you could ask, okay, but how about the second time derivatives? Where are the second time derivatives hidden? Any thoughts? Yeah? In the Lie derivative, they're right here. Okay. So you see, basically, with a little bit of good faith here, okay, that you could have anticipated at least the emergence of all of these terms just by thinking about what kind of derivatives we encounter. Okay, that's what we're getting. Okay, and again, basically, let's just take this at face value for now. I'd be happy to go back to this if we have some extra time and actually derive this with you. But I don't think it's for our storyline, it's not necessary. Okay. But what we see is that what naturally appears in this derivation are basically the spatial covariant derivatives, the Lie derivative, the extrinsic curvature. Okay. All the tools that we've developed. Okay. Now we have the decomposition of the left-hand side. How do we complete our story? Okay. Well, we complete this. Oh, by the way, one more part. We have, this is a vector equation. So basically, there's only one spatial part. We expect a spatial part and a normal part. This is the normal part. That's all we have for the normal part. All the other terms are spatial. Okay? So now, how do we complete our decomposition of the equation? We compare the normal parts of the left-hand side and the right-hand side, and we compare the spatial parts. Guess what? The normal part is really beautiful. Look, if I take the normal part of the left-hand side, the only part is that I'm getting here. On the right-hand side, I only have this. Guess what? The normal part of this gives us exactly the same constraint equation as we had before. Okay? So basically, let me write this down. We can now identify the normal part. That gives us the constraint dA, EA equals 4 pi rho. And then we identify the spatial part. And if I again rewrite the Lie derivative along n as the Lie derivative along alpha n as here, I use the same trick that we used here. Okay, and again, this is, you have to check that this is true. Okay, you have to believe me. Okay, and what you get then is the following: partial t EA equals dB of alpha dA AB perpendicular minus alpha dB A perpendicular A plus an alpha times EAK minus 4 pi alpha J perpendicular A plus the Lie derivative along beta EA. Okay, and this is the generalization of the evolution equation that we computed yesterday. Okay, all right. The key thing to remember is that when we look at the spatial decomposition of the tidal term, remember this is the tidal, the contracted tidal tensor, if you want to. It will have the spatial cousin of the tidal term plus these extra terms that accommodate the time derivatives. We'll see the exact same thing when we talk about the Riemann tensor in a minute. Okay? Are we good with that? All right. So again, why did I spend all of this time talking about E and M? Because it's not that our goal in the school is to talk about Maxwell's equations. Our goal is to talk about GR. But all the tools that we need to do the exact same decomposition in GR, we've already developed now. Okay, so basically all the quantities and objects that we need, we now have at our disposal. So now we can switch gears and we can talk about the same storyline for GR. So let's talk about the 3+1 decomposition of GR. So What changes? Well, the first thing that changes, we have a different field equation. Now, instead of Maxwell's equations, we have Einstein's equations. GAB equals 4 pi, 8 pi, even better, 8 pi TAB, okay? When we developed the decomposition of E and M, I basically invoked this electromagnetic Bianchi identity, and I argued that that tells us that there's one constraint equation and a one-fold gauge freedom. What is the cousin? And basically, what else did we get from that? We got the charge conservation, right? That identity gave us charge conservation, right? Now, what is the equivalent of that? It's the Bianchi identity in GR, okay? So basically, or strictly speaking, the contracted Bianchi identity. Which tells us that the divergence of GAB equals 0. In fact, that's how you can see how to construct the Einstein tensor from the Ricci tensor and the Ricci scalar. Okay, so this is by design. Just like in ENM, this identity has two consequences. One consequence is that if the covariant derivative or covariant divergence of GAB vanishes, so does the covariant divergence of TAB. That is what we mean by local energy conservation. Okay? So one consequence of this is that nabla A TAB equals 0. Okay? Also, you notice that these are four equations in the four-dimensional spacetime. Each one of those equations now tells us about a redundancy in the Einstein's equation. So there's now a fourfold redundancy. That means we expect both a fourfold gauge freedom and a fourfold or four constraints. Okay, so we now have four equations that are not independent. We might say that are redundant. That means we now expect four constraints and a fourfold gauge freedom. Okay. Different formalisms specify this gauge freedom in different ways, but mainly specified by making a choice for the lapse function and a choice for the three components of the shift vector. Those are your four gauge freedoms. Okay? They correspond, of course, to the fourfold coordinate freedom that we have in GR. Okay? Now, as before, what do we do next? Well, we developed a recipe. When we did this in EN, we developed a recipe for 3+1 decomposition. We said, well, guess what? First, we have to decompose our variables. Once we're done with that, we have to decompose the equations, and we're done. So now we'll do the same thing. Okay, so let's start by decomposing the variables. So as before, we'll proceed, we'll follow the same footsteps. Okay. So what is our variable? Well, our fundamental variable in GR is the spacetime metric. So how do we decompose the spacetime metric? We do it the same way as we did it, as we practiced in ENM. The variable GAB. Okay, so how could we formally do this? I could write GAB equals, okay, basically I insert two copies of the delta symbol. Then I write delta as G with indices up and down. Then I replace G with the projection operator plus NA and B or minus NA and B. So this is the same as gamma A, C minus NA and C times gamma BD minus NB and D times GCD. Okay, so now let's see what we get. Okay, basically, I first get the complete spatial projection of G. That will be gamma AC, gamma BD times GCD. Okay, then I get these mixed projections. Okay, so basically, I get this projection acting on this and then on that. But what happens if I do that? So let's say I act on this middle one. Okay. Then I basically, with this GCD, I could lower the index on the NC. That gives me an ND downstairs. You agree? Then I contract the ND downstairs with gamma BD, and that gives me 0, right? Because the projection operator acting normal vector is 0. So this mixed term gives us 0. You can check for yourself. This other mixed term also gives you 0. So the only term that's left over are the two terms here, okay? Now, what I could do is I can basically contract an ND with a CD. That gives me NC lower. Then I multiply the two NCs. That gives me a plus, a minus 1. That switches the minus into a plus, okay? So this gives me, am I doing, no, I have two minus, so I end up with a minus. So this gives me minus NA NB. Do you agree? You good? Right. Okay, so now what does this give me? Well, basically, I can use the G to lower this G, and then I see by the end of the day that this is the same as gamma AB minus NA NB. Okay, not shockingly surprising. Okay, so basically what this tells us that we can now define the induced metric, this gamma AB, which we'll call the spatial metric. It's just GAB plus NA NB. So the spatial metric, okay, which in fact is the same as what we previously called the projection operator. Except we now write it with both indices down. It's gamma AB is GAB plus NA NB. That gives us, that is the metric on our spatial slices. It's the same which previously we referred to as the projection operator. Okay? Now the next thing is we can realize that we can use this spatial metric to raise and lower spatial vectors, okay, spatial indices. So we can use this to raise and lower spatial indices. So for example, I could write BA, okay. Now formally, how do we raise and lower indices? Well, I need the space-time metric, right? So this is the same as GAB. This is, you know, non-negotiable. That is what we mean by raising and lowering index. But now I can write the GAB in terms of gamma and n's. So this is the same as gamma AB minus NA and B times beta B. But if beta is spatial, then the contraction with n is 0. So the only term that I'm getting is gamma AB beta B. Okay, this works for all spatial tensors. So whenever I have an index that is purely spatial, I can raise and lower it just with the spatial metric. I don't need to worry about the space-time metric. Okay. Let's also remember the following. We saw yesterday that if I write down the normal vector with the index downstairs, then I get a minus alpha 0, 0, 0. And I believe you explored that in the tutorial yesterday also, okay? Now, you agree that if I contract a spatial vector with n, I get 0. So for example, for the shift vector, I get this. I get NA, BA, that must be 0. But before I write down 0, let me write the only terms that I'm getting here, because the only non-zero term is the t component. So this is the same as NT. Beta t upstairs equals 0. And that means that beta t must be 0. Okay? So the general rule then is, if I have a spatial tensor with indices upstairs, then all the time components must be 0. Not true for the indices downstairs, okay? But it is true for the indices upstairs. So the contravariant, okay, i.e. the upstairs indices, okay, or time components, of spatial tensors vanish. Okay? And that means when we write down equations in the 3+1 decomposition, we can actually restrict all indices to just spatial indices, okay? All others will cancel out. Okay? So we can restrict to spatial indices. Now, different people use different notation for that. In mine, basically what I do is I use indices I, J, K, and so forth for spatial indices rather than A, B, C, D or so. Okay? So let's do an example. Let's actually write down the metric. Yes?
So you told that this contractor continuity leads to 4 constraints and 4 gates.
Yes.
So I didn't get how it comes.
Okay, so it's basic. What it means is, okay, right. That was a little fast. So basically, you agree that Einstein's equations are, we could count how many equations are there because the tensors are in 4 dimensions. We have symmetric tensors, so it's 10 equations, okay? And basically then you could say, okay, great. How many unknowns do we have? Well, our variable is GAB. By the same argument, there are 10 independent components GAB. So you could say, great. Basically, we have 10 equations for 10 unknowns. We are done, right? Just like yesterday, we argued similarly in ENM that there's 4 equations for 4 unknowns. And we thought, great, okay? Except yesterday, we realized that, well, there's the electromagnetic equivalent of the Baumgarte identity, which told us that actually one of the equations is not independent of the others. So really, we only have 3 equations, which meant that basically we can only determine 3 of those variables, and one basically we have a freedom there, okay? So in other words, we argued that one of the equations is not independent, it is redundant, it acts like a constraint equation, and by the same token, we have a freedom to determine one of the 4 variables, that was the gauge freedom. Now it's the same thing, we start out with 10 equations for 10 unknowns, we realize that 4 of the equations are not independent, they're constraint equations, meaning we only have 6 equations. That means that we can determine, from the equations, we can determine only 6 of the 10 independent components GAB, leaving us with 4 that we can choose freely. Those correspond to the gauge freedom. Does that answer your question? Is that what you meant? Okay, great. Yeah, good question. Yeah. All right, should I erase it now? Okay. Yeah. So the contravariant components of a spatial tensor need not be 0.
Yeah, that's it.
Okay.
So only when the indices are upstairs, only then you think we restrict them to spatial indices.
That's right. Okay. Now you could ask, okay, why is it then true that we can do this everywhere? Well, because indices could either appear paired with a lower index, so in a sum, okay, basically if they're dummy variables where a sum of all of them, they're paired with one upper index, so the time components are automatically 0, you can ignore them. Or you could say, well, maybe they're free indices, okay? But because if it's a spatial tensor, that gives you a constraint, so you can, there might be a non-zero time component, but you will never need it because you would always get it from the spatial ones, okay? Yeah. Mm-hmm. Okay. Yes. I'm sorry, I couldn't hear you. Say that again. How did the time components of the spatial tensor? What?
How does the time component exist in a spatial tensor?
Okay. So you're confused. Why am I telling you that the downstairs time component might be non-zero? Is that right? Right. Because basically, if I wrote this the other way around, maybe I'll do it over here. Okay, so basically, let's say I looked at this term, okay? Now, basically, remember the upper components of n, even the spatial components may be non-zero. So basically, this would be there's an nt beta t plus an ni beta I, okay? And it's only the sum that can be zero. So basically, even if this is non-zero, it can be canceled by these terms, okay? So basically, we don't have the same constraint here that the sum is restricted only to the time parts, and therefore, basically, we cannot use the same argument to make a statement about the beta lower t. Does that make sense? Okay, good. All right, let's work out what the metric is. Okay, so here's an example of what I meant by restricting to spatial indices. The inverse metric is gamma AB minus NA and B. Okay, and basically gamma is a spatial tensor. So if one of the two indices A and B is just has a time component, then this term must be zero, meaning that the spatial parts of the metric are given only by the contributions from n. Okay, so that means I can write this as the time component will be given by nt, strictly speaking, the minus nt. That gives you a minus alpha to the minus 2. Likewise, the space time components are, this one is again zero. I only get contributions from that. This will be an alpha to the minus 2 beta, beta I. And the same thing here. I get contributions from the gamma only for the spatial parts. So the spatial part here would be gamma ij minus alpha to the minus 2 beta I beta j. Okay? So that is the form of the inverse metric in terms of our 3+1 quantities. Now I can take the inverse of this metric to get the metric with the indices downstairs, and that then gives me the following form. Yes. Yes. Okay, this minus, the minus sign is correct, but it should be up here. Okay. Anyway, right? It's alpha to the minus 2. Yeah, sorry. No, it's of course wrong. It's just in the wrong place. Yeah. Okay, so now we invert this. And then we have GAB equals, okay, what you would find by doing that is minus alpha squared plus beta L, then we have a beta I, and a gamma ij. That's what you would find by inverting this matrix. Okay? And if this is the metric, then we can also write this as the line element. So the line element is then GAB, DXA, DXB, and that we can write as minus alpha squared, dt squared, plus gamma ij, dxi, plus beta I dt, times dxj, plus beta j dt. Okay? So this is how we can write the line element. Now we can draw a picture similar to the picture that we wrote yesterday. Okay? In order to interpret what this metric means, it's sometimes called the ADM form of the metric, or the 3+1 form of the metric. So yesterday we drew basically one slice at coordinate time t, then we had a second slice at coordinate time t plus dt. I started by taking a point that has certain spatial coordinates xi. I drew a normal vector, and if I take the normal vector multiplied with d tau, then basically that points up there. Now, except what I'll do is I'll write the d tau as alpha dt. So this is alpha NA dt. That is this vector. It takes us to this point. Okay. Now, this point we recognized yesterday may not have the same spatial coordinates. To get to the corresponding point that has the same spatial coordinates xi, I would have to add an extra leg, which is given by beta I dt. Okay, right? So now Basically, this would be the path that would take me from the same spatial coordinates in one slice to the next. But of course, we may also have basically a different. We may want to measure the proper distance between two space-time events that have different spatial coordinates, maybe this event and that event. Now, basically, this event will have spatial coordinates that are maybe xi plus dxi, meaning that this extra vector here gives us the shift in the spatial coordinates. Does that make sense? Okay. So what then is this vector? This vector here is the sum of beta I dt plus dxi. So let me write dxi plus beta I dt. Okay? You with me? So basically, what is then the proper distance between these two space-time events? I could use, if you want to, a space-time Pythagorean theorem by adding the proper separations in two orthogonal directions. One separation is this one. That separation is given by alpha dt, okay, squared. Then I need to take into account this separation. Well, that separation will be dxi plus beta dt squared, if you want. That's exactly what we're doing here. Okay, so we can interpret this line element as giving us like a Pythagoras, okay, which gives us this proper distance plus this proper distance squared plus this proper distance squared gives us the square of that one. Okay, and then we throw in the minus sign for good measure because this is not a Euclidean space. Okay. Make sense? All right. Now what we could do is we could practice. If we're given a space-time metric, then we could now figure out what are the laps and the shift and the spatial metric and all of that for this particular metric. Here's an example. On the tutorial on Monday, you transformed the Schwarzschild metric into isotropic coordinates. You did that actually twice. The first time was on slices of constant Schwarzschild time. Let's compare with that metric. What you found there was that ds squared equals minus 1 minus m over 2r divided by m plus m divided by 2r squared dt squared plus 1 plus m divided by 2r to the fourth times dr squared plus r squared d omega. Okay. In this case, it's quite simple to identify what the lapse and the shift and the spatial metric are. First, you notice that there are no mixed space-time terms. There's no term like dt, dr, or anything like that. So we immediately see that the shift must be 0. Okay. Then we can look at the dt squared term alone. We see that this must be alpha squared. That means alpha by itself is just 1 minus 2m, m over 2r divided by 1 plus m over 2r. Okay. Finally, we identify the spatial metric. Well, that's just this term. Okay. So that means the spatial metric, gamma ij, equals 1 plus m divided by 2r to the fourth times the flat metric, gamma ij. All right? So this is a simple example where you can identify the lapse and the shift. It's a little bit more complicated if the shift is non-zero. But good news, you get to practice that too. Because remember, in the other exercise on Monday, you transformed the metric into a form where there was a non-zero dt, dr term. So guess what? This afternoon, you get to practice how you identify the shift for that type of metric. Okay? So basically, you can always do that. Of course, this is, if you want, a little bit backwards because we're given a space-time metric. And then for the given space-time metric, you can identify the lapse or shift in the spatial metric, which is very useful for testing purposes, for example. But in a real numerical simulation, of course, you don't know the space-time metric yet. So instead, you impose some condition for the lapse and shift to figure, to construct the space-time. We'll talk more about that on Friday. Okay. But now let's finish this story. Well, it'll still take us a little bit, but let's see, where are we? Now, the next thing that we can do is we can show the following. Show that. Okay. It turns out, basically, if I computed the Lie derivative of the spatial metric gamma AB, okay, then I would write this. I could use the definition of the Lie derivative. Actually, so far we've defined it, we've used it only for rank 1 tensors. We could look up what is it for rank 2 tensor, and then we would find we could write it as NC times the nabla operator, NC AB, plus gamma CB, nabla A and C, plus gamma AC, nabla B and C. Okay, and if you basically work out what that is, I'll just report the result to you, but I think I assigned that as an exercise also. It's actually not too hard. If you work this out, you will find that this is minus 2 KAB, the extrinsic curvature. Okay, so now that is kind of neat. What that means is that, so previously we talked about the extrinsic curvature in terms of the rate at which the normal vector changes from one point to the other. But now this gives us a whole new interpretation of what the extrinsic curvature is. Namely, we can think of the extrinsic curvature as being related to the derivative of the spatial metric along the normal vector. But because the normal vector points to the future, that's like a time derivative. Right? So basically, the extrinsic curvature is related to the time derivative of the metric. Okay? Now that's kind of neat because what you see then is basically in these equations, A was our fundamental variable, and E was essentially the time derivative of our fundamental variable. Our fundamental variable is now the metric. Then you see that K plays the same role here as E does here. Okay? Did I say that the right way around? E is the time derivative of our fundamental, K is the time derivative of the fundamental variable, just like E is the time derivative of the fundamental variable here, okay? Okay, so basically you see there's a parallel thing going on here, okay? Now we can use the same trick that we used before, and I think that you asked me about, okay? I could now say, I can multiply this with the lapse. We write it as the Lie derivative along the lapse times n. And then that allows us to write it in terms of Lie derivative along the vector t. That gives us just a partial derivative of t. And this tells us that by the end of the day, this is just the time derivative of gamma ij, gamma ij equals minus 2 alpha kij plus di beta j plus dj beta I. Okay? And in fact, this equation plays the same role as this equation in E&M. Look, it's the time derivative of our fundamental variable equals minus a new auxiliary variable, if you want to, which is now the extrinsic curvature. Here we had a gauge term. Okay, guess what? Here's a new gauge term. It's exactly the same form. Isn't that lovely? Okay. All right. Now it's time to actually talk about it. Okay, fine. We defined the spatial covariant derivative, but how can we actually evaluate it? And it turns out we can evaluate it in exactly the same way you would evaluate the covariant derivative in space-time, except you compute the Christoffel symbols from the spatial metric only. Okay. So my claim is that we can compute the spatial covariant derivative of any vector from partial I, Vj, plus Vk. And notice now I'm writing the Christoffel symbol without the 4 in front, because now I mean by this a spatial Christoffel symbol that is computed from the spatial metric in exactly the same way you would compute the Christoffel symbols from space-time metric. Okay, so this is computed from the spatial metric. It's now a 3D Christoffel symbol. Okay, and should you believe this? No, you should check it for yourself. And in fact, I'll ask you to do that in the tutorial this afternoon. You can check it for yourself, and you'll see basically how do you check that? You could compute it from the covariant derivative in 4D. Then you write the metric in terms of gammas and n's, and then you'll see that all the normal vectors cancel out. Okay? And that leaves you with this. By the same token, we can also compute a spatial Ricci tensor, Rij, which is computed from the spatial metric in the same way you would compute the 4-dimensional Ricci tensor from the spacetime metric. So there's a gamma, KL, and then there are all these partial derivatives, partial K, partial L, gamma Ij, plus partial I, partial J, gamma KL, minus partial I, partial L, gamma Kj, minus partial K, partial J, gamma IL, plus terms that are now in orders, it's quadratic in these spatial Christoffel symbols. Okay? So basically, you can define the same thing. What do we have to do next? We've done defining all kinds of variables. We've decomposed our variables into spatial and normal parts. Now we need to decompose the equation. Okay? And basically, at the heart of Einstein's equations is the Ricci tensor. Okay? So we need to decompose the Ricci tensor into spatial parts and normal parts. But it works in the same way as an ENM. Maybe 15 or 20 minutes ago, we stared at, if you want, the Ricci equivalent in ENM. We said it has second derivatives, both in time and space. Therefore, we expect that basically the equivalent derivative, spatial derivatives, that was the spatial cousin of the 4D case, plus all these extra terms that accommodate the time derivatives. Now, if we decompose the Riemann tensor, the 4-dimensional Riemann tensor, they're also both spatial and time derivatives of the metric. The spatial derivatives we can accommodate in the spatial equivalent of the 3D Riemann tensor. Okay? But where are the time derivatives? Well, guess what? The time derivatives will appear in terms of k in the extrinsic curvature. So we should already expect that when we decompose the 4-dimensional Riemann tensor, we will get terms that are this 3-dimensional Riemann tensor and extrinsic curvature terms. That's exactly what happens. So let me write this down. So but what we'll do, or what I'll quote to you, are the decompositions. We now decompose the 4-dimensional Riemann tensor, R, A, B, C, D. Okay? And basically, now let's think about how many different possibilities do we have. Okay? So we could get a completely spatial decomposition of this, projection of this, right? Then we have 4 indices, right? So then we could have 3 spatial, 1 normal, right? We could get 2 spatial, 2 normal. This is scary, there's lots of them, right? There could be 1 spatial, 3 normal. But actually, what happens when we contract this with 3 normal vectors? What will we get? Why do we get 0? Because of the symmetries of the Riemann tensor. Remember, this Riemann tensor has these weird pairwise anti-symmetries. They save our butt, basically, okay? Well, okay. Anyway, that means that if we have more than 2 normal projections, we will automatically get 0. So luckily, we get only 3 different projections: space, space, space normal, and normal, normal. Let me write down those equations, okay? So basically, if I have a completely spatial decomposition, by the way, for the spatial decomposition, never mind, no, never mind. I'll get back to that. So we have 3 different ones. We have a completely spatial. That gives me what is known as Gauss's equation. Okay. And that is gamma IP, gamma JQ, gamma KR, gamma LS times PQRS equals RIJKL. So this is the 4-dimensional Riemann tensor. This is the three-dimensional Riemann tensor, okay? Plus KIK JL minus KIL KJK, right? That is the completely spatial projection. Then the next possibility that we have is one normal. Okay, that gives me the so-called Kodatsi minority relation. And that is gamma I P, gamma JQ, gamma KR, and S times RPQRS equals, now basically here we have derivatives, spatial derivatives of KIK minus DIKJK. Okay, remember that K contains time derivatives on the metric. So if we now take a spatial derivative, these terms give us mixed time space derivatives of the metric, which would be hidden in this contraction of the Riemann tensor. Okay? And finally, we could take two normal decompositions, two normal projections. That gives us Ricci's equation, namely gamma I P, gamma JQ, and R and S times RPQRS equals, we would find that this is the d derivative along the normal of Kij. Kij, think of this as the second space derivative of the metric, right? Plus 1 over alpha di dj alpha plus Kik kkj. Okay, so these are the three equations that we're getting from this projection. Up to now, this is purely geometry. We have not invoked any physics yet. Okay, so the next term, the next step would be, actually, before we do that, let me tell you, obviously I'm not deriving this, okay? There's a fair bit of math that goes into the derivation of that. I happen to know about textbooks where you can read on that, okay? But basically, I don't think it's particularly good use for our time to go through that in detail, okay? So instead, let me just quote this, okay? But now, basically, the next step that we need to do is we need to use these equations in Einstein's equations. So basically, these are just the decompositions of the Riemann tensor. Now we compute the traces of these terms, because the traces of these terms enter into the Einstein tensor, and then we insert those traces in the Einstein tensor, and that gives us the decomposition of Einstein's equations. Okay, and when we do that, we get the following. Actually, maybe I'll do it over here. So we finally insert this into Einstein's equations. And then we get basically, again, three types of decompositions: normal, normal, normal space, and space, space. Okay. The normal, normal projection actually, let's remember what happened here. When we took a normal projection of Maxwell's equations, we got a constraint. We won't be shocked if this also gives us a constraint. Okay. And in fact, it does. It gives us the so-called Hamiltonian constraint. Yeah? Yeah, sorry.
Shouldn't the normal surface be connected to Q and S within RMS?
You know what? I think you're right. Did I copy that? RS? You know, yes, I think you're right. Actually, I don't have a way to look it up right now, but I think you're right. I think these indices are misplaced because that would give us 0. You're right. You are absolutely right, and I apologize. It actually might, maybe this is a Q and this is an R, but you're right. Actually, it's the wrong placement. Okay, so this is probably wrong now. Let's decorate this with a question mark. Okay. Check that, okay? I copied that wrong down. It's wrong in my notes too, but you're right. Yeah, I'm sorry about that. Okay. All right, but now basically if we take the normal projection of Einstein's equations, we get the Hamiltonian constraint, which we can write down as the trace of the spatial Ricci tensor plus the square of the trace of the extrinsic curvature, which sometimes we call the mean curvature, minus Kij equals 16 pi rho, where this rho, by this rho we now mean the contraction of the stress energy tensor with a normal vector. In other words, this is the energy density as seen by a normal observer. That's the Hamiltonian constraint. Then we take a time-space projection, or normal space projection. That also gives us a constraint, namely the momentum constraint. Which we can write as d I of Kij minus gamma ij k equals 8 pi ji. Okay, where this ji is defined as minus gamma ia nb tab. Okay, this is the energy current density or momentum density as observed by a normal observer. Notice that this constraint looks very similar to this constraint. Because how would you describe this constraint? You'd say E is the time derivative. E is the same as the time derivative of our fundamental variable. That the constraint tells us something about the divergence of this variable equals to some matter density. It's the same thing here. Kij is the time derivative of our fundamental quantity. And it's the divergence of this time derivative, which is related to a matter quantity. Okay, so there's a direct correspondence between the momentum constraint and Gauss's equation in E and M. The last equation that we need to talk about is the space-space projection. Okay. So the space projection, which gives us the evolution equation. Namely, what we will find is that the time derivative of Kij equals alpha Rij minus 2 Kj plus Kij minus di dj alpha minus 4 pi alpha, and then what I'll call mij. These are matter terms, plus the Lie derivative of beta of Kij. And this mij is the same as 2 times Sij minus gamma ij S minus rho. Okay, and what the heck is that? Well, Sij I defined as the projection of the stress energy tensor, i.e. gamma IA, gamma JB, TAB. Okay, it's the stress observed by a normal observer. Okay, so this is the evolution equation. And actually we should put boxes around these equations. Okay, so here's our evolution equation. This was our Hamiltonian constraint. And here is the momentum constraint. Okay. And basically what you now notice is that basically, and I already erased one equation, which I'll now put back on the blackboard again, which we found by identifying the time derivative of the metric, which was, we previously found this, partial t gamma ij equals minus 2 alpha Kij plus, actually, I could also write it as beta, Lie derivative of beta of gamma ij. Okay, so now we see that together these equations are called the ADM equations. Where are they? after Arnold, Desser, and Misner. Okay, so the Arnold, Desser, Misner, or short ADM equations. Okay. All right. Notice that they take exactly the same form as our Maxwell's equations, right? This equation we can think of as just defining the extrinsic curvature in terms of a space-time derivative of our fundamental variable, just like basically we can think of the E being defined in terms of the derivative of A. Then we found a constraint equation. The Gauss's law is very similar to momentum constraint. Because we have this extra set of constraints in EMN, we have, in addition, the Hamiltonian constraint, but also notice that the evolution equation for Kij, okay, which we think of as the second time derivative of our fundamental variable, has very similar terms to what we found over there. This one term is the Rij. What is Rij? Remember, Rj are all the mixed second derivatives of gamma ij. It's kind of like these mixed second derivatives of Aij here. So these two terms play the same role as the Rij here, right? That's where the second derivatives are hidden, okay? So that's the same term as there. Then we have matter sources. There's a 4 pi j there. There's a 4 pi m over there, okay? So that is the same. Notice that that structure was already the same as the scalar wave equation, except we're kind of building up and making it a little more complicated for every extra index. Now you could ask, but what the heck about these terms? But remember, this is for a general space slicing, a general slicing condition. When we re-derived these equations a minute ago, but I had to erase them, okay, to make room for all of this. When we re-derived this, we also had these extra terms in this equation, which involved the extrinsic curvature, okay? And those actually was a product of E and K, for example, but E is the same. What plays the role of E now, we see is the same as K here, right? The E is K plays the role of E, okay? So when we had EK previously, there would now be a K squared. That's exactly what we have here. Okay? So basically you can see how the same terms emerge, and we can really think, rather by being overwhelmed by all these different terms here, we see, actually this is very similar to what we saw before. We shouldn't be shocked to see all of these terms, okay? So that's what these equations are, okay? And we see basically that really they're similar in terms of these equations. I told you before, once we have the equations in this form, we know how to implement them on the computer. We could evolve them, okay? At least in principle, okay? That leads us to what we need to talk about tomorrow and on Friday, namely how do we solve them numerically? And basically you can already anticipate we'll do that in 2 steps. Basically, remember on Monday we said laid out what we want to do. We want to lay out how do we solve these equations numerically. We want to do it as a Cauchy problem where we have data at one instant of time, and then we want to know how we can integrate them forward in time. So the first step will be how can we get our data at the first instant of time? That's what we refer to as initial data. We cannot choose those, unlike for the scalar field. For the scalar field, we could choose arbitrarily. But here already, you see we cannot choose them arbitrarily because our E field has to satisfy this constraint. Likewise, now basically our initial data will have to satisfy these 2 constraint equations. So what we'll talk about tomorrow are strategies for how we can solve these constraint equations so that we can build initial data that satisfy Einstein's constraint equations, okay? That is on our to-do list for tomorrow. Then on Friday, we'll talk about the next step, namely, once we have the initial data, how can we evolve them forward in time? There's still things to do. It turns out that these equations don't work so well when we implement them on a computer. So we'll talk about why that might be. How might we fix it? Also, then you asked, well, what about the lapse and the shift? What do we do about those? So we'll talk about what are good choices for the lapse and the shift. That's what we'll talk about, among other things, what we'll talk about on Friday, okay? That's where we are. We again covered a lot of mileage today. Thank you for listening. And that brings me to the end of what I meant to talk today, unless you have any questions that you would like to raise right now. Okay, thank you.